Great. Thanks for everyone joining today. So we're gonna discuss 9 factors that impact your PCB designs, from material selection, a little bit about stack-up design, and then shielding and thermal management. But before that, if you haven't reached out to Sierra for a quote, I encourage you to do so. We're an ITAR NIST certified PCB manufacturer and assembly facility located in Silicon Valley. So we do all sorts of technologies there. And please reach out to us. You can go to our website, start a quote there. We'd love to work with you. Neil, do you want to talk about this slide?
Yeah, sorry about that. Yeah, so I'm Neil Jarvis. I'm an application engineer with Rohde & Schwartz. I've been in the RF and microwave industry for about 25 years. So we really have 3 categories of products. Test and measurement, which is kind of the area that I work in. We make products for testing wireless products, cell phones, wireless LAN, Bluetooth, that kind of thing. ICR, so components for signal integrity, components that go into wireless devices, things like that, backplane testing, things like that, and then aerospace and defense, so things for testing satellite communication, satellite links, things like that, and then automotive. So we have some interesting products for testing radars, radar performance, automotive radar echo generators. Then we have a technology systems group, so where we basically take these boxes and put them together, put software around it, put some infrastructure, so you can see some of the systems down below, where we're taking stuff, putting together and using our technology expertise to solve a larger problem. Could be aerospace defense. We do a lot of signal integrity and EMC, EMI. We're kind of the leader in the EMI area. And then we have network and cybersecurity products. So looking at endpoint security, secure network communications, etc. And one other area that's not mentioned in here is we actually make stuff for quantum computing. That's an area I've kind of gotten involved in more recently. So we have products for testing quantum computing. So if anybody's into that or interested in that, ping me afterwards. And that's all I got.
All right, thank you very much. So let's dive right in. So first, we'll discuss the parameters to consider when choosing materials for your RF PCBs. And again, I encourage lots of questions. We have engineers and people standing by to answer them. And if not, we'll be getting back to you with the answers. So please, make this engaging and ask a bunch of questions. So first, the dielectric constant, I think, is a very key place to start. So the dielectric constant material will directly affect how quickly a signal travels through a PCB. So as the value increases, the signal propagation speed will decrease. And then with the higher decay, there's more you're more prone to inductive and capacitance coupling. And a couple other points, the trace impedance is inversely proportional to the dielectric constant. And, we recommend using materials like iSpeed or tachyon, with a lower decay. Next would be the dissipation factor or loss tangent, which measures how much signal loss occurs in a dielectric material. And a higher DF means basically more signal loss. And this results in increased attenuation and greater insertion loss. So for an optimal performance of your RF board, again, material selection is really important. Like a Rogers 4350, an Itera, a Megtron. If you go with the PTFE materials, which a lot of you mentioned, there are definitely manufacturing challenges with that. First, solder mask is very hard to get to stick to that. And also even the plating within the via. There's an outside process to roughen up the material in order to process. So that just be aware of it, takes longer and costs more because of that. Very kind of hazardous process to roughen up the surface of the materials. Then the other important aspect of the material is copper roughness. And so the main thing that material vendors have offered is low profile coppers. So there's also foils that go through reverse treatment. And then, that's up to you. You can talk to us to understand what what copper types does that material vendor offer. And we'll be happy to suggest what we feel is a good solution. You also have to worry about peel strength of copper. So if you use some of these materials, you have to understand the peel strength might decrease. And so again, we can run some tests and give you some input on that. So next is the CTE and thermal conductivity of the material. So you want to always select a material that has a CTE that closely matches the rest of the board, because as things expand and contract, it's and they go through the repetitive thermal cycling. This is where different CTEs will cause the mechanical stresses, and that will definitely cause an impact in the field. And even prior to field, if you go through some testings on the bare PCB, you can see failures there. So next on thermal conductivity, a high thermal conductivity material is essential to prevent components from overheating. So for effective heat dissipation, consider thermal conductivity greater than 0.5 watts per meter Kelvin. And here are some example materials that we work with regularly that can meet that objective. So another important aspect of RF circuit boards is designing a reliable stack up. So we're going to dive into that. So, let's explore why a hybrid stack up is, could be potentially beneficial for your RF circuit. So a hybrid stack up will ensure, your control impedance requirements and a solid return path for your RF signals. And it also allows to incorporate low dielectric constant materials, only for your RF layers. And that basically will, save you cost and hopefully ease the manufacturing side of it. And so if you can build up your hybrid stack up with these different types of materials, you're kind of getting the best of both worlds. And if you want to build up your sensitive RF circuits and isolate them from the rest of the board, you can, mix and match the materials that way. And so what we've seen in hybrid stack ups is basically two material types. Maybe a 370 HR or a Ventec or something like that. And then on the outer layers where the RF features are, that's where you have your, low decay materials. Sometimes, depending upon the material type, it makes it a little bit more difficult to manage the manufacturing recipes like drilling and plasma and scaling. But more or less, once we run a design or a hybrid stack up once, we'll get the scaling information. So just be aware of that sometimes a board fabricator might need to run a first article to dial in those types of things. So here's some key strategies to ensure high performance. Your high performance stack up. So next, designing the traces to ensure signal integrity. So here are some essential design techniques to enhance your signal integrity in RF circuits. First and foremost, you want to minimize the length of the RF traces. Second, avoid running your RF traces in parallel to other signal traces, just to avoid any unwanted coupling. And then here is an example of a daisy chain instead of multi-point branches, and so on and so forth. So next I want to talk about the via design. So from a design rule perspective, if you have vias that are mainly there for, connection, you can have a different type of design rules for that, which maybe the manufacturer is okay with, like a tighter vias, but you also have to be, aware of any manufacturing constraints that the PCB manufacturer may have. But I think it's worth discussing with them specifically on their tolerance of vias and the purpose of the vias. Where in the past, a via is a via, and there's no need to discuss that with the manufacturer. I think in RF designs, it becomes important to discuss those things with the manufacturer. So you can use smaller vias with diameters between 8 and 12 mils, and smaller vias can help minimize parasitic inductance. And as you distribute your vias along both sides of the transmission line, you want to definitely evenly spaced to provide a consistent grounding path. And we have a calculator for that. I'm not sure. I don't think we're doing a demo of that today. So next is impedance matching techniques to reduce the reflections. So you want to modify trace width, thickness, and clearance to achieve a uniform impedance across your PCB. So wider traces would result in lower impedance. And you can use a transmission line stub, either open circuited or short circuited, to fine tune the impedance. And a transmission line stub can be adjusted in length and position to achieve the desired impedance. And then lastly, you can incorporate termination resistors to reduce reflections. And then below are the common types. So now I think we have a demo. Vandana, I'll hand it over to you.
I will share my screen now. So Sierra Circuit's impedance calculator uses the 2D numerical solution of Maxwell's equations for PCB transmission lines and renders fairly accurate results. The impedance calculator tool supports 82 impedance models with multiple geometries, such as the coated, uncoated, embedded microstrip here, or stripline 2. And with each of these specific models, you can choose single, differential pair, or coplanar over here, etc. This tool is also integrated with the signal loss crosstalk and the S parameter calculator. We'll start with a coated microstrip in a differential pair for now, and the simple and the composite pair over here are both displayed. Let's go with the simple model for now. The tool also allows you to change units if you want to. You can use this drop down here to do so. We'll go with mils for now. Enter a dielectric constant height here. Let's go with 3.348 mils. A dielectric constant of 3.63. Coating height H1C of 1.5. The coating height H2C and ER2 here are both already entered, but you can change it if you wish to do so. Let's go with 1.5 for coating height H3C mils. If you want to calculate the trace width, you need to enter delta W. Delta W is the difference between the top of the trace and the bottom of the trace. You can click on this help button here And a table will be displayed that suggests delta W values based on the starting copper weight. Let's go with 0.5 for now. Enter a trace thickness of 1.45 mils and 6 for the trace separation. Let's enter target differential impedance 100 ohms and click on calculate W. The trace width and the other calculators will be calculated and displayed here. You could also do a reverse calculation if you want. Enter the trace width and then you can calculate the differential impedance too. Now let's go to the signal loss calculator for the same chosen geometry. Enter dissipation factor, frequency for about 10 gigahertz, a surface roughness of, let's say, 6 microns. So this is a standard roughness for a foil, and 2 for the length, 2 inch. Now click on calculate loss here, and the signal loss for the odd and even mode, both will be calculated and displayed. Similarly, you can use S parameter and the crosstalk calculator for the same model. Thank you so much.
Thanks, Vandana. Guys, I don't see too many questions. The way we know the webinar is appropriate is definitely with questions. So still encourage you guys to ask away. Okay, so I think another important topic is your ground planes and the designing of ground planes. So when you have a specialty material, more copper is easier for the material to stick to, especially when the material itself is a PTFE. So having ground planes, not just for the electrical and RF performance, but also for the mechanical performance of the board, is really critical. So I just want to throw that in there. But proper grounding is definitely crucial for maintaining your signal integrity and minimizing interference. You can have the technique of, a dedicated ground plane for each RF layer. And of course, a continuous ground plane is the best. So you can avoid your impedance discontinuities. If you want to implement via stitching along the edges of the ground plane or around the RF traces, that's also a good idea. And to do that, follow the rule, which is the via to via gap should be between lambda by 20 and lambda by 10 to avoid any overlapping and interference. One other common technique is to put ground pores on the top and bottom layers. It will shield and be helpful for EMI. And just be aware of your ground pores. And cross hatching is not as easy to deal with on the PCB manufacturer side. So a solid ground pore is better. Some other potential strategies to prevent interference. You can use the Faraday cage to shield the RF components or sections. So that would help to block external EMI. You can incorporate conductive shields around sensitive circuits, which would act as a barrier, again, for any kind of unwanted EM radiation. Make sure you connect those to ground. And then when you're working with microstrip lines, the situation can be slightly different since the top side lacks a ground plane. Connect the via fencing on the top layer using a trace. I think we have time for one more demo.
Yes.
Okay.
So we have the power distribution network analyzer tool here. This tool determines the target impedance, fastest rise time, and the maximum frequency for a PDN based on power rail voltage, maximum power rail current, the acceptable voltage ripple, and the switching current here. To use the calculator, you enter the power rail voltage Let's go with 3.5 volts and 2.5% maybe as the acceptable voltage ripple. Enter 1 ampere for the power rail current and let the switching current be 80% of Imax. Now click on calculate here and the target impedance will be calculated. You can click on this second calculate button and this will calculate the maximum frequency for 0.5 nanosecond fastest rise time. You could change this value here or you could also use this drop down to calculate the fastest rise time by entering the maximum frequency. Click on Save to Table button and the calculated power rail will be displayed on the table below here. You could now do the calculations for a fresh power rail. Click on this Export to Excel button and the table will be downloaded. The power rail network in your circuit board layout should ensure a stable power delivery. The high switching speeds can lead to voltage fluctuations, crosstalk, and EMI in the system and hinder the performance and reliability of the PCB too. These challenges can be overcome by maintaining the power supply's AC impedance below a target impedance. And our tool helps you to do just that, to optimize the power delivery network in your PCB layout. Thank you.
Okay, thanks, Vandana. Okay, so a little bit about the thermal management. So you want to incorporate thermal vias and cooling fans to facilitate heat transfer and spreading.
Amit, hold on just a sec. We can still see like a black bar at the top of your, at the bottom of your screen.
Okay, hold on. Better?
Thanks. Yeah.
Okay, great. So for thermal management, you can design your 12 mil diameter or 0.3 millimeters with via to via spacing of 0.8 millimeters or 31 mils. You can use heat sinks made of thermally conductive materials like aluminum or copper. You can put aluminum in the center of your board as well. I've seen that done and still have plated through vias. And you can, also, there's just a few techniques which are written here. And then important DFM rules. I'm not going to go through each one line by line, but it's, I mentioned a few already that, solder mass becomes a challenge with specialty materials. Roughening up whole wall for plating after drilling, that becomes a little bit difficult. Also, what are the feeds and speeds of the drill also change a lot. And so you just have to work with your manufacturer and make sure that it's a material they're comfortable with, that they have the recipes. And if it's a hybrid, expect a little delay with the first article that needs to be run. And then here's another kind of slide to be as helpful as possible, which would be, some proper fab notes to include in your RF design. And again, I think it's really important to share some functionality of what your board is going to be doing. And the example I gave before was, okay, what's the purpose of these vias? The more information you can share on the performance of the board, the better, and gives the fabricator a lot more context. I think I'm going to stop sharing and have Neil take over from here.
Okay, so signal integrity. So signal integrity kind of typically is really addressing more high-speed digital stuff, but not necessarily. I mean, I'm an RF microwave guy by trade, very much a VNA person. Actually wrote a VNA book with somebody. It's published by our tech house. But a lot of these things are really common, whether it's RF or high-speed digital. And it's really more the language that people talk. Signal integrity people talk in the time domain. They talk about eye diagrams and things like that. RF and microwave people don't. They kind of talk S parameters and things like that. Anyway, so quickly about me, I'm an applications engineer with Rohde and Schwartz. I've been in the RF microwave communications, everything industry for about 25 years. I'm kind of an expert, I guess, in VNAs and phase noise measurements. So I do a lot of that kind of stuff. So clock jitter, things like that. And I've been with Rhody about 12 years. So feel free to reach out to us if you need any help with anything or have any questions that I can address. Okay, moving forward. Okay, so here's a good example. You know, high-speed digital stuff tends to be really the worst case scenario for a lot of these things, because if you kind of go back historically, when people made in the beginning computer stuff, they weren't really thinking about reflections and mismatches and stuff to the degree that somebody who's an RF and microwave person. So just the architecture of things is dramatically different. So as a really good example, if you look at a PCIe Gen 5 board, you'll see there's some kind of BGA component on the left. You can see one of the balls connects to a via, probably a blind via goes down. Actually, it's not a blind via. A via goes all the way down. You see there's a strip line trace buried and comes back up. There's a capacitor. You can see there's daughter cards. Those cards have more BGAs on them and more buried traces and things like that. So it's super complex. All of these interconnects, vias, traces, BGA, solder points, connectors, etc. They all are potential issues with signal integrity and mismatch and things like that. So that's really the thing that we're trying to isolate. And you see here for the spec on the PCI Gen 5, you know, the loss budget is 36 dB. So that's going to come up with some other issues, which I'll talk about in a sec. Okay, so historically, the way you would test a PCB would be with a TDR. So basically, I send a signal out. It's a pulse, square wave, and it leaves the instrument, goes through the device, perhaps a cable or something like that. Oops, it's going off on its own. Okay, so and I'm looking for the reflection. So I'm looking for the signal that comes back. And as it comes back, I'm going to measure the signal that returns, the amplitude, how much it's changed, as well as the time at which it took to go and come back. So from the time, I can determine where on the board it is. So that's kind of historically, particularly the kind of board fabrication houses have done this. But oops, sorry, somehow I'm in auto mode. So that's typically how this has been done. But as we come to these higher frequency devices, there's tending to be some other issues, which I'll talk about in a sec. Okay, so what can I measure with a TDR? TDR, it's a time domain reflectometer. It's a measurement technique that observes the behavior of reflected electrical waveforms. So typically a square wave through some homogeneous medium. You know, typically we're not looking at like active devices. So we can look at cable fault locations, distance to fault, impedance measurements, and mismatch, strip line, etc. Sorry. And some of the signal integrity things we're going to look at: rise time, balance link performance, crosstalk, etc. And we might even want to look at eye diagrams. Okay, so the key thing to think about in TDR relative to something like PCIe, if you look at the loss budget, we said 36 dB, right? That's a fairly significant amount of loss. And when you're looking at high-speed signals, to get a high-speed signal, you know, perhaps picoseconds, you need a lot of bandwidth to generate a square wave, right? So in order to have a lot of bandwidth, it means my noise floor is higher. So my instrument, to determine the noise floor, it's 10 times the log of the bandwidth of the signal, right? So if I have, you know, a megahertz signal, I'm going to take KTB, which is minus 174, and then I'm going to add 60 dB, right? 10 log of 186 is 60 dB. So now my noise floor went from minus 174 up to minus 114. So now I can't measure anything lower than that. And, you know, realize that no instrument is really down as low as minus 174. And you'll find that the wider the signals, obviously, if I go to a gigahertz wide signal, it gets, you know, 30 dB worse, et cetera, et cetera. So So what can I do about that? Well, if you look at a VNA measures not using square waves, it uses sine waves. Okay, so sine wave, I can have as narrow a sine wave as I want because it doesn't have any harmonic content, right? A square wave, again, is odd harmonics of sine waves to generate a square wave, and the rise time is really based on the highest frequency sine wave you have in there. So what I'm going to do with a VNA is I'm going to look at this in the frequency domain. So I'm going to measure, instead of measuring 135 gigahertz, for example, together as a square wave, I'm going to measure the 1, the 3, and the 5 separately, and then I'm mathematically going to put them together using an inverse Fourier transform. So from that, I can calculate the step response. So it allows me to have really arbitrarily narrow bandwidth. So that's kind of the big thing you've found as the frequencies have gotten higher. We have things that are getting into hundreds of gigahertz in terms of clocks and things like that. Okay, so if you look in a VNA, and this is kind of my thing, you see it looks somewhat similar to the TDR I showed earlier. We have there's a source you see on the left, but this source is a sine wave. It's a very clean sine wave. Goes in, there's a signal separation, so that's what we call a directional coupler on the input and output. And basically from this, I'm going to look at the sine waves coming in and out, similarly to what I did with the TDR, and I'm going to measure the relationships between those. And if I want the time domain response, I'm going to take this frequency domain response and convert it to the time domain. Okay, so when I do that, again, this is all just going to be math, which will be not shown to you. You don't have to worry about it, but it's what's going on in the background. But looking at resolution, so how narrow a wave I can, look at is really dependent on what's the maximum frequency of my VNA, right? So there's a pulse there, and if I look at in the frequency domain, I have a limitation based on the maximum frequency. So, you can see there that what's the distance and time I can measure. It's dependent on that. Okay, then we get the unambiguous range. So this is basically how far can I look based on the number of points that I have. So, I send a signal out, I'm waiting for the return. And if I see multiple returns, obviously, if I'm waiting too long, I'm going to see the next return before the first return. So that's a consideration in terms of setting this up. And here's kind of the formulas for it. And obviously, these will be available in the end. Okay, so the next thing is low pass and band pass mode. So when we're doing this, basically when we're looking at this, the device typically is a trace on a board, right? It might be a trace with a via or connector, but we're typically not looking at band pass devices, things that have lower frequency cutoff, higher frequency cutoff, particularly lower frequency, which provide challenges in terms of doing this mathematical representation. So typically for all the things you're going to look at that we're talking about here, we're going to use the low pass mode. And I'm not going to talk about band pass mode in the interest of time. But if you're interested, you can ping me. So basically, the point of low pass mode is I get the negative and positive frequencies, and that's a Fourier thing. So, go review your Fourier mathematics if you want to get into that. But basically, we'll set up this frequency grid, and you have to tell it what is the other end impedance, right? And the reason for that is because the analyzer, no vector network analyzer goes down to DC. They all have some lower frequency cutoff. In the case of the instrument I'm going to show you, it goes down to, I believe it's 9 kilohertz. But so you have to tell it what the DC value is. So when we set these up, which I'll show you in a minute, you're going to tell it that, we're going to set it up, and then we can go back and forth between the time and frequency domain. Okay, so so here's looking at what the response might look like. If you look at the top, you see a trace. It's on a FR4 PCB. There's a trace and a via, another trace on the bottom, and then a via back up and another trace. So if you look at the impulse response, you see as I get to the beginning of that via, there's some reflection there, right? Then at the back of the via, there's another reflection. So you see two reflections there, same thing on the other end, and then you see one on the other side. So if you look at the impulse response, you just see spikes at those particular frequencies. Most TDR type of people typically want to see the step response, which is what you see below, but it's really kind of the same information. It's the change from one value to the next. So one of the things that you might want to do, if we go back to this and we see all these things, maybe I want to look at just this second via by itself, right? So there's a thing you can do with a VNA, which you can't necessarily do with a TDR. It depends on the TDR, but basically there's a thing called gating, right? So I can go in here and say, like, I want to look at just this via on the right. So I'm going to put a gate around that time where that occurs. So then the analyzer will mathematically remove all the other reflections. So as an example, if you wanted to look at what is the input impedance of that via on the right, as seen from this trace on the bottom, I can use the TDR gating feature to remove all the other responses. So that's a pretty neat feature that you can do, and I think some TDRs might have that too. So here's kind of just in the end an example of something that you might see where we have a microstrip, and this is coming more from an RF guy perspective. You know, we see different impedance traces. So it's a 50 ohm, a 75 ohm, a 50 ohm, and you look at it just as a function of real impedance, right? So I see there's a spike at the beginning and end of that transmission, variation, et cetera, okay? And there's kind of the formulas for finding the range and whatnot. Okay, so I'm gonna do real quick, I'm gonna switch to my VNA and just show you, let's see. Okay, so here is, basically this is a cable. So I have a cable, just an RF cable connected to a port 1 of my VNA. So when you set it up, you'll see here, I go in and I look at S11, right? And the key thing when you set these up is setting up the frequency grid. Again, I want to make it so I have the complex impedances. So when I go in here and I look at time domain to set up the time domain, I want to have this low pass step, right? So in order to have the low pass step, I need to have a harmonic grid, and it'll complain to you here if you don't have a harmonic grid. So you can tell it to adjust it, but what I typically do is I set the start and stop frequency, whereby I set the start at some, let me go back to the frequency domain. So this is setting it up in the frequency domain before I switch to time domain. Trace. Okay. Start. Okay, so I'll set the start frequency. I just sort of arbitrarily picked 10 megahertz. I didn't want a really narrow grid to make it go faster. And then I put the stop frequency at the max. And then you make the step size, so sweep step size, the same as the start frequency. So that pretty much guarantees you a harmonic grid. So when I look at this, at the time domain, so if I go back to trace, time domain, when I turn this on, I don't get an error because it'll tell me that the grid is harmonic. Okay, see up here, it says the current grid is harmonic. So that's good, that means it's happy. So when I do that, now I'm in the time domain, but in this case, we probably usually want to look at the real impedance of the trace. So if we do Measure, we can go Z S11, and that gets us to this. So this is, I just had done this ahead of time. So now I'm looking at distance. So on the horizontal axis is distance, and you see here it defaults to time domain, and that's typical in any VNA. You can tell it I want it in terms of distance as opposed to time. You'll have to put in the dielectric constant of the material if you want to have that accurate. But anyways, so and you can see here, if you look at the trace, you can see it's basically 50 ohms, and you see a transmission. The end of the cable is an open. So you can see here on the left, if you look at, so I'm going to zoom in on this. Stop. I don't know. 5. Yeah, no. Okay, you see that little blip. So the front panel of the VNA, and it's not calibrated because I wanted to be able to show this. So you see there's an N connector on the VNA connected to an N adapter to an SMA. So you see there's a few little blips in there because there's some mismatches going on. So if I look at that, that's a mismatch. And perhaps if that was at the other end of a cable or a trace on a board or something, which I don't have immediate access to, I can actually go in and turn on this gating feature. So if I do trace and I go to time gate, right? When I show these range lines, you can say like, okay, I just want to see at this point, at this connection, and I want to ignore everything else, right? So when I turn it on, you can see it flattens everything else out. So everything else is more or less 50 ohms. So I'm just looking at that. So, and now I might even want to go back to the frequency domain. So I can go to time domain and switch that off. Now you're seeing that is the real impedance in the frequency domain at that particular point. So that's kind of a nice feature. You know, I can do a similar thing where I have a differential impedance. I'm not going to go into this in a lot of detail, but you know, when you set this up, you will do measure, and you see here I can set up balanced ports. So you're basically saying I want differential in, differential out, or something like that. And you know, when you set up, I'll show another trace because somebody I think had asked this. When I do balance ports, I can do this, and I can say measure all S parameters, right? So this is showing you differential, so that's SDD, differential to common mode, that's a conversion on a particular port. And so those are all the various differential and common mode S parameters. And you know, you can obviously also do single-ended on those 4 ports, and you can get from one to the other. Okay, so I'm going to go back to the slides. Hopefully I can get it out of this auto mode. Okay, so the next thing is you guys might want to look at something somewhere on the board other than the connector point. You know, when you're troubleshooting, it'd be really great if we just connected up the board and it worked end to end. But if that happened every time, then we probably all wouldn't have jobs. So, so you know, you're probably at some point going to have to go in and look at the thing somewhere along the signal path, right? So in the case where somebody had asked a question about I'm not getting my LAN connection, maybe automotive Ethernet or whatever on the other point, you know, you basically need to establish, do I have a signal path from one end to the other? So in the simplest case, you're going to say, I'm going to get an ohm meter, right? Is it even connected from one end to the other? Well, obviously, if that's not connected, then it's not going to work. So the impedance mismatches and whatever don't even matter. So that's kind of the first step. But then if you've established that you have continuity between the two, you know, then you're going to have to start stepping through things, right? So for me, when I used to do circuit design, and I did it quite a bit, and I did system level design, you know, I would try to strategically put test points along the board or places where I could populate a connector that's clean that I can go in and look at it later. Maybe like an LO output that's going into a mixer or something like that. So that's kind of something just planning ahead when you're designing a circuit. The next thing is solder on probes. So, in all said and done, maybe you don't have room to do that, or maybe something happens somewhere other than where you had anticipated. So I have to solder a semi-rigid onto the board. That's definitely something you have to do. But typically less accurate than the left. There are high impedance probes. Typically as you're kind of moving along, this is a little less accurate. But then on the far right hand side, we really have matched RF probes. So we work with a company called Packet Microwave. They've helped us with a lot of stuff. And you can see here, those are manipulatable probes. So, there's a probe on the left and the right. That's what they look like. They have single-ended differential, and they're not the only manufacturer, by the way. And you can go on, and you'll have a microscope also. So the microscope's showing you the fine pitch, what's going on, where I can manipulate the probes. You have to planarize them, get them flat, and then you can go on and measure things. They have probes up to 67 gig. I know there's another guy that has stuff up to 110. So, it's certainly possible to do that. Obviously, the higher in frequency, the more considerations you need to make for things. But anyways, so that's kind of what a whole probe system might look like. You might have a manual microscope. You might have a dyno light microscope, things like that. So those are all possible. And, the process is really very similar. You can either cal to the end of the probe tips using something like here, that calibration substrate. So that might have a short open load kind of thing. There's other means of calibration. Or you might cal to the coaxial interface, and then you have an S parameter file for the probes, whereby you'll de-embed it. And, things where we have a differential probe that doesn't have a ground plane on it, we're probably going to have to de-embed it. Okay, and then, so the next thing, I talked about, I want to measure, these places. So perhaps I want to go and measure that input port to that, that silicon package on the right, but I don't want to include the lead-in trace that's buried with the VN, all that kind of stuff. So obviously one method I can use is the TDR, but the challenge with the TDR is it's not as accurate in terms of getting a full S parameter file and knowing the exact length and whatnot of that trace. So if you want a super accurate characterization just of the trace, so I can move that reference plane, I can use these de-embedding tools, right? So they typically talk about the lead in and the lead out, right? So the lead in is basically the trace from the connector to the place where I want to measure. And then the lead out is from that point on the output to the connector. Okay. So I'll calibrate with the coaxial standards at the coaxial interface. And then I'm going to use one of these software tools in the firmware, which I'll show you in a minute, where I can measure these, generate an S parameter file. Then I add that mathematically from the reference plane to the point on the board where the DUT is that I actually want to measure. So kind of the process of how it works, and we have 3 different tools for doing this, and I won't really discuss necessarily all the differences, but the one most commonly used is ISD. That company at Titech, they've been around for a long time. It's kind of considered the most accurate of any of these. And incidentally, if you've been using like an ENA or a PNA from our competitor who changes their name every couple of years, and I used to work there, so they have a thing called AFR, automatic fixture removal. So anyway, so what we'll do is you'll typically have a fixture, which is obviously your device, right? and you have a test coupon. So the test coupon basically is taking the input and output traces and putting them together, right? So first you're going to measure that, right? And then you're going to sort of tell it something about the characteristics of what that lead in and lead out are. Are they equal in length at the input and output? Are they different? Or perhaps you don't have this setup here. Maybe you just have the input or output trace, whereby you're perhaps just removing the DUT from the board and then measuring the trace on the unpopulated board. That's another way of doing this. Not quite as accurate, but it still works pretty well. So from that, you're going to run this algorithm on the VNA, whereby it's going to say, measure the coupon. Then you're going to measure the DUT with the coupon, which is really your device, and then tell it to calculate the fixture model, right? So it's basically, once you've done that, it generates an S parameter file, puts it in place for you, and you go on your merry way and make your measurements. And there's kind of, this is sort of what it looks like. Measure the coupon. So this is assuming a symmetrical in and out, and I'm doing a 2x through. So that 2x means the input and the output added together of equal length. So there's fixture left and fixture right. So this fixture you see here is from the IEEE P370 standard. So you measure those two combined. That's the 2x through. Then you put the DUT in. In this case, it's a Beatty transmission line. And then with the input and output, then you run the tool, and then you measure that by itself, and then you'll see the device by itself with those traces. So I don't have a device handy, but I'll just show you on the VNA kind of what it looks like. So let me just connect one just so it's not looking quite as hinky. Okay, so again, not calibrated or anything, but if I go in and I'm going to say, let's see, offset. So offset embed. So that's basically meaning I have something other than just the trace. So there's a variety of different models. You can tell it, I just have some electrical delay or loss at some number of values, where it would just do a straight line approximation. Typically, I haven't seen anybody really use these above a few hundred megs, so really haven't been used probably in about 10 years for the most part, but it's one way that you can do it. But what we'll do though, is we're going to do this single-ended. So there's a similar differential one. We're just going to do single-ended. So what you'll do when you go to single-ended, it basically asks you, what does your network look like? And you can tell it, I have, this component values, but typically you'll go to a 2-port network. So I'm going to actually measure it. I'm not going to just assume some ideal values. So we come in here, you tell it which tool you're running. We'll start with ISD. You run tool, and here you're going to tell it, what do I have? I have a symmetrical 2x through. So if you remember, that means that the trace from the connector to the input of the DUT is equal to the trace from the output of the DUT to the connector. But you might just have a 1x open. A 1x open would, for example, be, I don't have a test coupon, but I'm just going to take an unpopulated board and I'm going to look at that input by itself. You could also do the same thing, short 2 of those and then have a short, or you can do 1x open short, which is obviously better than just doing a single. So you'll just measure that. You have to select the ports. So I'll do 1 to 2. You'll measure it. And then once this is completed, I don't have a good DUT in here, so it's probably not happy. Then you're going to basically remove the DUT, or remove the coupon, put the DUT in, and then you're going to run ISD. And that will generate the S parameter file for the input and output networks and populate it into the analyzer, and then you can continue on measuring, whereby now you're going to see the result whereby the where is that? Oops. Yeah, where we've now moved that reference from the connector, say on the left here, to the input to the trace. Okay, so that's all I have. And we can go ahead and look at some questions. I'm gonna stop sharing.
Okay, great.
Okay, so let's see. So hopefully I think we answered your question on the first one about the 2-port LAN. If you have another question, please follow up. Okay, regarding what frequency to use for calculations with your calculator. So this is to you guys, but I'm sure I'll have an opinion. Is there an advised process to use in order to calculate the effective frequency, the knee frequency, as some call it, of a signal given high frequency components, rise, fall, etc.? So I'll just say my 2 cents, and then you guys please chime in. So they're saying like 100 kilohertz square wave. So I can tell you, like, from the customers I deal with, the people like a Cisco or a Google or something like that, they pretty much know. Like, you're like, I'm doing a 20 gigabit signal, so I need 10 gigahertz is my fundamental, but then I want a third and a fifth. And they're realistically not knowing they're not going to go beyond that. I mean, typically with these higher speed things, if you get, 2 odd harmonics, you're doing pretty well. Just if you look at all the connectorization and everything like that. So that's my 2 cents, but, Amit, please chime in if you have further comments.
Vandana, do you have anything to add?
No, Lucy.
Okay, great. We can go to the next question. Claire, you have my email, so if you need more clarification, you can email me.
Okay, so next one's for you guys. Thermal stuff, I got no comment.
We have Steve Carney with us. He's the director of our R&D department, so maybe Steve can help.
Awesome.
Steve, do you see the question?
Yeah. I'm trying to find it here.
I'll read it. Do you have supporting data for thermal performance using the 12 mil-vias?
We'd have to look at the stack up in the design to try to figure that out. Has to do with spacing and material thickness and internal coppers and all that kind of stuff. So,
yeah, not a simple answer. I think it's
no, not a simple answer.
Yeah, right. Yeah. So call you for more info, right?
Yeah.
Okay, so I'll just keep reading these off. Victor, so how does PCB potting encapsulation material properties, DKDF, affect your calculations? That's to you guys again.
Unfortunately, we don't have any experts from our tools right now on the call. But what we can do is we can get answers to that question later. I will post on Sierra Connect.
Okay. Yeah, and I mean, I just my 2 cents. I think that's probably going to be. I know, like in your one tool where you were calculating the transmission line impedance, it did seem to have values for that. So that would be my expectation. It's kind of an EM model where it's looking sort of like a strip line, but not.
Okay, thanks.
Sure. Okay. How do you connect the ground to the chassis? So, I mean, yeah, I mean, typically for, RF kind of things and, really high-speed digital things too, like you know, ground is sacrosanct, right? So, you know, it depends a lot on your configuration, but you know, often grounds are all tied together, and you just want as much common ground as you can. You guys might have a comment on this, on kind of digital ground versus RF ground. In my experience, a lot of times they're all tied together, but I know there's an issue sometimes where if you have like really high-speed digital signals, you don't want them tied to the RF ground because it actually lifts ground above 0 volts sometimes when you get high currents. So yeah, not a simple answer. Okay, how should we design a transition between RF track to pad of an IC where there's a large discontinuity? Let's say IC pad is 1.2 million. I'll let you guys answer that, but that's a really good question, in my opinion.
Yeah, I'm going to defer to the design team to answer offline.
Okay, I'll just make a quick comment there is, you know, from the RF perspective, you saw when we're looking at TDR, we're looking at discontinuities, right? So, I mean, really, if you think about it to some extent like a hose, right? If you take a hose and you put it, you connect it to a smaller hose, you know, typically you want things like beveled, so it's kind of looks like a funnel, right? As opposed to, you know, more of a jagged connection. If you look at like the EM simulation, you'll see like you get much more radiation. The fields are bouncing around a lot more. So it should look kind of more smooth. That's kind of typically what it looks like. But I'll let you guys get into more detail on that. Sorry, I always have an opinion. Okay, moving on. Okay, instead of tracing an antenna to the entrance of an IC, could I just solder a coaxial cable next to the pin and not worry so much about shielding, since the coaxial cable has its own? I plan on using IPEX MH4 cables connection. I'm not familiar with that cable, but you know, RF ground, you just got to be really careful. You know, when you have any potential between different grounds, it's really going to add a lot of noise and impedance issues. So, you know, all I can say is in general, the most problems I've seen in any of the boards that I've ever designed, and I've done quite a few, most commonly are grounding issues where you don't have enough ground around a component where the voltage rises or things leak out through the ground. So just be real cautious and make sure things are really clean. If you're using a coaxial cable, make sure you have a really clean interface, you know, ideally a connector or something like that. Okay, 2x coupon and the use of the channel de-embedding and how it compares to 1x. So I think I did talk about that, but I mean, basically, you know, what the 2x through does is, and when you go into the math, it's going to give you nightmares about like when you took vector calculus, if you're an engineer, and eigenvalues and eigenvectors and whatever. I did a paper on this a while ago, and I still have nightmares because I don't remember a lot of that math. But basically what it does is it takes this three-dimensional matrix or two-dimensional matrix, and it's going to take, it's going to look at, you know, what is the loss and reflection coefficients of that 2 or 4 port network, and it's going to just divide it in half, right? So when it does that, it's assuming that it's perfectly on the input and the output, and they're exactly symmetrical. So when you then put the DUT in, as opposed to just the 2x through, it actually goes and looks in the time domain for reflections and things which are different from the perfect value, right? So when it does the perfect value, it assumes it's exactly half the length and loss, and then it goes and says, okay, what do I actually measure, as opposed to what the perfect value was, and it calculates the difference between the two. So that's sort of the magic of those algorithms. So when you do a 2x, obviously you're measuring the input and the output when you do the DUT plus the coupon. So obviously, because I'm measuring both, I get a more accurate value. When I just do the 1x, I'm assuming that that one is symmetrical. So I think that hopefully that answers the question. How do you measure the VSWR of a microstrip antenna and record the data? So measuring the VSWR of an antenna, basically, and it kind of depends on what the interface is. It's a good question, but it depends. If you said, I have an antenna on a board, and I have a SMA connector on the board, obviously I just measure it. That's probably not what you mean. So, the key thing is going to be getting from a measurement point to the DUT, i.e. the antenna, and isolating them. So you would need to basically find some file that you can de-embed between the antenna and the connector. And without looking at it, kind of hard to answer, but the antenna has to not be there when you do that de-embedding, create that de-embedding file. So how do you calibrate a VNA to measure a 2-port antenna? So when you calibrate a VNA, always it's just a 50 ohm cal. Like I think there's actually is a 75 ohm cal kit, because years ago the cable industry does stuff at 75 ohms instead of 50, and that's a whole nother conversation. But anyways, but everything you do is going to just be a 50 ohm cal. Even when you do a 4-port where you're doing 100 ohm differential measurements, they're really just 50 ohm cals. It's not a separate cal kit or anything like that. So it basically does the 50 ohm cals, and then it mathematically calculates the 100 ohms. So, so I'm assuming you mean a 100 ohm antenna. So it's simply just do a multi-port cal. If you were just looking at S11 or SDD11, you do a 2-port cal, put it in differential mode, and measure it. It's as simple as that. And by the way, if any of you guys need help with something, you're welcome to email me. I don't remember if I put my email on here, but if not, I'll make sure you have it. How does the price of a TDA, I think you meant TDR, compare with that of a network analyzer? I'm not super up on TDRs, to be honest, but I would venture to guess the network analyzer is more expensive. It always depends. Like, we make ones that are less expensive, and then we make ones that are really expensive. We have one that goes up to a terahertz, and as you might imagine, that's pretty pricey. Probably, as much as a house in some places. But then we have ones that are, kind of 10 grand. So, it really depends on the frequency. But in general, I would say TDR is probably less expensive, but you don't see them as frequently anymore. A lot of the guys I work with who use TDRs, they're using stuff that's really old. So it's an interesting question, though. I know actually our scopes have a TDR built in too, so that's something to check out. But I'm not a scope specialist, so okay. What SMA type connector do you recommend for strip line circuits? I'm looking for an easy solder and RF reliable connector. So, I don't know, do you guys have a recommendation on that?
Our design expert had to go, so I will get this answered on Sierra Connect.
Okay. Yep. I don't have anything specific there.
And yes, I will share the presentation after this webinar.
Yep. I figured. Okay. Okay, good. We're getting near the end. Okay, how should we design transition between RF track and a pad of an IC if there's a discontinuity, let's say width of an RF track? So I think I mentioned that earlier, and I think you guys are going to follow up. Maybe you have some more technical answers to this, but I can tell you again that I've done like an EM simulation where if you look where you have a very discrete transition where it looks like, a right angle, for example, versus sort of a smooth transition where you're kind of looking like a hose kind of thing. The smooth transition is much more effective. So you typically want to try to make that kind of like a funnel. I guess that's the simplest answer to that. But you can do an EM simulation and get, kind of the idealized value if you want it. What layer stack up should be followed for better PCB strength and ways of increasing? So I'll leave that to you guys.
Okay. Oh,
You talking about just thermal stress strength, or
I think they mean mechanical. Please
Yeah.
correct me if you're wrong, but that would be my assumption.
I mean, really, it's really what somebody needs. We do so much of this now that we don't really have issues with different materials. As far as like a lot of the PTFEs, they contain fused silica already, so they're using a lot of filler, these types of materials.
Right.
It comes down to the different types of bond plies and prepregs that you're gluing all the layers together with. So there's been a lot of advancements in those materials in the past couple of years. So we really don't see problems. We pretty much build what a customer asks for, and we haven't seen too many problems.
Yeah, that makes sense to me too.
Occasionally we'll get into some weird internal, like somebody wanted aluminum plating.
Right.
We struggled with that a little bit, but we figured out how to do it. So right now we don't really see anything that's significantly better than one way or another.
Yeah, I mean, it seems to me like the FR4 kind of material is so well understood. Probably trillions of things have been built on it. I would imagine that's pretty.
Yeah, and even the PTFEs that we've built so much of that these days, and they've made so many advancements and making it easier to deal with that we don't really see much issues with the different materials.
Yep, that makes sense. Okay, that's all I got. Anybody has any other questions? And incidentally, I'll just mention it. My email is neil.jarvis@rsa.rodi. In fact, I'll put it in here. -schwartz.com. We have kind of an annoying email, but here's mine. neil.jarvis@rsa.rodi-schwartz.com. That's me. Feel free to send me an email if you have any questions.
right, got it. Wow, that was a very long webinar.
Sorry, it's hard to shut me up sometimes. So
that was really great. It's always amazing when we have that many questions. So thank you very much for everyone who posted questions, and Neil, thank you very much for these very cool demos and for answering all the questions.
Yeah, my pleasure.
Thank you.
Yeah, thank you very much, guys.
Thanks, everybody. Have a good one.
Bye.
I'll send you updated slides too. Thanks.
Thank you. Have a good
Thank
one.
you.
Bye.
Bye.